Okay. And then in terms of topics we're going to be covering today, we'll be covering the 2019 final exams, specifically the question of basically all of the questions. And those question topics are firstly hydrostatics, and pulleys, then trusses and design calculations, then 3D reactions, and finally shear and bending moments. Yeah, I'm Bo. You can find me on my Facebook on William Bo Zhao. Just search me up if you need any general problems or like advice on how to do final exams or any kind of school related things. I'll be happy to give you advice on that. Awale Omar, one of our other presenters, Masbin Kareem, Fiad, and Vishal. So now that we got our introduction out of the way, firstly, Fiad will be talking about hydrostatics and how to basically go through the process of solving a hydrostatics question. So Fiad, you want to take it away?
Yep, sure thing, Bo. Let me just present. Just one moment. Okay. All right, so I'm Fiad, my name is, and I'll be presenting the hydrostatics question to you guys today. So let's read through the question and let's see what we have to do. The wall ABC is 8 meters wide, perpendicular to the paper, and is used to retain salt water. It is held in place by a fixed support at A and a cable at B. Segments AC and BC are connected by a pin at C. Determine the reaction forces on the wall at A per unit length of the wall. The density of salt water is 1,050 kilogram per meter cubed. Okay, so it seems pretty simple. They want us to find the reactions A and divide by the width to find per unit length. But let's draw a free body diagram and let's just see what's really going on with this little aquarium to see how we can really finish this question. So this is the free body diagram of the entire gate. And as you can see, there are 3 pressure forces, one created by this triangular prism, 2 created by this half rectangular prism, and there are 2 because I don't want to have to find the centroid of this shape. So I just broke it up into 2 composite shapes, a rectangular prism and a triangular prism. And each of them produce their own force. Outside of the 3 pressure forces, there are 4 unknown. A moment at A, because it's a fixed reaction, and 2 reaction forces, one in X and one in Y. And then also a tension force at BD because it's being held up there. So because there are 4 unknowns and we only have 3 equations of equilibrium, that means we have to take a section somewhere because we can't solve this, it's statically indeterminate unless we do. So I think the best place for us to take a section would be at C, and that's because there's a pin there. So that means when we cut it there, it would only produce 2 reactions, okay? And if it only produces 2 reactions, then if we look at the section BC, it would only have 3 unknowns, TBD, and the 2 reactions at C. And once we find those 2 reactions at C, we can further proceed by looking at the section CA. Because if CX and CY are known, we also know F2 and F3 because they're pressure forces and can be calculated. So we can just find MA, AX, and AY using our equilibrium equations. Okay, so let's get started with the actual process. So this is the section BC, and this is a bit of a free body diagram showing the distances, okay? Anything blue with a blue line is submerged underwater. Now, something I immediately notice is they give us that this is a 3, 4, 5 triangle, okay? So they give us these lengths initially, 3, 4, and 5, and that means anything on this angle will also have proportionate measurements. So another length they gave us was 1 meter, and from this 1 meter, we're able to come to the conclusion that this base here would be 4/3 meter and 5/3 meter would be the hypotenuse. That's because 1 meter is 3/3, and proportionate to that, this would have to be 4/3, and the hypotenuse would have to be 5/3. Alternatively, if you guys are not great with similar triangles and you can't solve it just by looking at it, you could find the angle of inclination, which I still do, and you can just use trigonometry to find any unknown sides. Okay. Now let's calculate the pressure force. So we know the force of this prism is essentially the volume of this triangular prism, with the base being the pressure at the bottom. So the force will be 1/2 rho GH times the width into the paper times the length of the gate. So that's 1/2 1050. You know, we work it out and we see that the first pressure force is 618,030 newtons. Now after that, we're going to need to find the angle of inclination of the gate. And this is because we need to break the pressure force into its X and Y components. Okay. So the angle of inclination of the gate can be found using arctan of 3/4, opposite over adjacent. And from that, we're going to have to do 90 minus that because the angle in which this force is on is equal to 90 minus the angle of inclination. It's opposite, okay? So once we find that, we do 90 minus 36.87. We could find our F1x and our F1y using cosine and sine respectively, okay? So F1x comes out to be 370,819 newtons, and F1y comes out to be 494,423 newtons. Now, dealing with the location of these forces, we know that the force will be located to 1/3 from the base of a triangle because that's the centroid of it. Now, if it'll be 1/3, the entire the amount of gate that's submerged underwater is 5 meters. So it would have to be located 1/3 of 5 meters above sea. Okay, so to do that, we would just multiply 5 times 1/3, and we would see it's located 5/3 meters along CX. And from that, we can find the horizontal and the vertical sides to be 4/3 meter and 3/3 meter, just like how we did with the cylinder triangle. And once again, if you're not comfortable with this, with using cylinder triangles, you can always use the angle of inclination to find these distances. Okay. So after we found the distances, we can take a moment about C, and we use the moment about C to calculate TBD. But one thing we do is how the moment will be taken along the gate, and that's because F1 is perpendicular to the gate. TBD is also perpendicular to the gate. So we can take the moment along the gate and not have to use the X and Y components of F1. So taking the moment along the gate with only the forces F1 and TBD, well, the moment along the gate at C, sorry, we would have only F1 and TBD in this calculation. And we would see TBD comes out to be 154,508 newtons. Okay. After this, we can finally solve for Cy and Cx using our sum forces in X and our sum forces in Y equation. And this can be done because we know TBD, and that can also be broken into its X and Y components. And I sort of do it in one go with the equations. So for some X's, I use the X component of TBD and the X component of F1. And for the Fy equation, I use the Y component of F1 and the Y component of TBD. From this, we get Cx is 278,114 newtons, and Cy is 370,819 newtons. Now that we know Cx and Cy, we can move on to the second section. So this is a free body diagram of the second section, and like I said, since we know Cy and Cx, there's only 3 unknowns. So we should probably begin by calculating the F2 and F3, the pressure forces due to this prism. So F2 is simply the volume of this rectangular prism. So this can be calculated by the pressure at the top times the width into the paper times the length of the gate. So using all of that, we can see that the pressure of the rectangular prism, the pressure force provided by the rectangular prism is 1,483,272 newtons. And now we have to calculate the triangular prism's pressure force. So the base at the bottom here, it's going to be the pressure at the bottom minus the pressure at the top here, okay? So that's going to be rho G9 because the total depth, if you look at the original question of the tank, is 9 meters underwater. And the total depth at the top here is 3 meters. So the pressure at the bottom minus the pressure at the top would be rho G6. That would be the sum, okay? So we can multiply this by the width into the paper, which is 8 meters, and the length of the gate, which this portion of the gate is 6 meters, okay? And since this is a triangle, it's all multiplied by 0.5. And we see that F3 is actually equal to F2, and they're the same pressure force, 1,483,272 newtons, okay? As for the distances of these forces, well, F2 is provided by the rectangular prism, so it'll be located at the rectangle centroid. And that's half the distance, the length of the gate, okay? So it would be 3 meters from point A. And like I said, since the triangular force is at the centroid, or 1/3 meter from the base, or 1/3 from the base, I'm sorry, then it would be 1/3 times 6 meters away from point A. So that would be 2 meters, okay? Now that we have all the distances and we have all the forces, we can start using our equations of equilibrium to solve for AY, AX, and MA. So solving for AY first, we can see that there's only two forces in the Y direction, AY and CY. So summing them, we'll see AY is equal to CY, and that means AY is equal to 370,819 newtons. To solve for AX, we would have to sum up F2, F3, and CX, and we'll see that that is equal up to AX, meaning AX is equal up to roughly 3,244,658 newtons. And finally, for the moment at A provided, because it is a fixed reaction, we would take the moment at A and we would use all of the forces that are not along the line. So we would disregard CY and we would only incorporate F3, F2, and CX. And we can see that the moment at A is equal to negative 985 million and 44 Newton meters. Now what this means that it's negative, it means it's in the opposite direction. I assumed it was counterclockwise just based on that being positive, but this moment is clockwise. Now we have to remember the question asks us for the reactions per unit length of the gate. Usually this means we would divide by the width. We would divide every force and reaction by the width, if whatever they're asking for. And this is just because the force at the bottom is distributed along the width, not along the length of the gate. So once we divide AY, AX, and MA by 8, we will get the corresponding correct answers. And at the bottom, you can see that AY per 1 meter is 46,352.4 Newton per meter. AX per meter is 405,582 Newton per meters. And MA is 1,135,630.5 Newton. And that's because the meters cancel. No, meter squared. Sorry, I forgot to put Newton per meter squared there. But yeah, and these are your final answers for the questions. If you guys have any further questions as to how I solved this problem, please feel free to put it in the chat. I'll make sure to answer it. Okay.
All right, everyone, just give me 1 sec. I'll be doing the next question, okay?
Okay, in case you were asked to find the location of F2 plus F3, I think you're asking me what the location of the force provided by the entire trapezoidal prism. You'd have to find the centroid of that prism, and there's a specific formula on it. I'm pretty sure you would just sum up the shape centroid times their area and divide it by the sum of their areas. Correct me if I'm wrong, guys, but I think that's the formula. And that would be the location of the centroid. And that would be the location of the trapezoidal force. Is that what you were asking, Aziz?
Let me just share screen for you again, if you had, so you can maybe explain it that way.
Yeah, so because we don't know what the centroid of this shape is, or maybe you guys do and I don't, you'd have to use a formula to take the centroid times the area of these shapes separately. So the area of this rectangle times its centroid, and the area of this triangle times its centroid. And you just divide it by the sum of the areas, and that's it. For trapezoids, it's just like triangles for the centroid.
All right, cool. If
Yeah,
that's that,
probably go.
we'll move on to our second question of the day. So this question is going to be on frames and pulleys. So it's all, just take a second to read the question. I'll read it with you guys. So determine all the forces acting on member ABC of the weightless coplanar structure shown below. Present your answers on a summary sketch of member ABC. Just a few things we want to just determine initially. Will be we're only asked for forces acting on point A, point B, and point C, as in member ABC. So really try to gear our solution towards what's the fastest way to just find what we need. So there might not be a need to find every single force in the frame. Let's just try to figure out what we actually need. And finally, present your answers on a summary sketch of the member. So all this means is instead of just having AY, BY, AX, whatever, all over your page scattered about as you solve them and hoping the TA finds them, we're just going to draw a line, write A, B in the middle, C on one side, and just write have arrows with the magnitudes of each forces right beside that, okay? So just a nice little free body diagram, basically, to have our final answer with, okay? So let's get straight away into solving the question. So here's going to be our 4 steps towards solving this problem, okay? So first, we're going to look at global equilibrium and see what we can solve with that. 2, we're going to use relevant parts of the frame to get close to the answer. So that's exactly what we were just talking about earlier, which is solve only what you need to solve for, okay? Then 3, we're going to follow a logical series of pieces when solving. So we might need to go in a certain order. We just have to think about that logically, and I'll explain to you guys how we can do that. And finally, we're going to solve for the forces on ABC. So remember what we're solving for, ABC. So as soon as you get something there, try to move on if you don't need to solve for any other force, okay? Don't waste your time solving for stuff that won't be marked, okay? So right now, this should be fairly simple. I have a picture of the question in the corner. I'll have that throughout. And we just have a simple free body diagram redrawn, okay? So this is easily 1 out of 12. You'll get if you just draw this with the reactions. Notice AY, of course, roller. This should be very simple for everybody now, okay? So first thing we can off the bat notice is that if we take sigma fx, we can tell, oh, look, there's only one force in the x direction, dx equals 0, okay? That should be very easy. Next, we need to find AY or dy. So we can take any option we want. We can take the moment at D or the moment at A, and then we can solve from there. So I chose to do sigma md. We set up our equation. This should be very simple for everybody, okay? I don't want to really get into the details of it. You guys can look at that on your own when you have some more time, okay? After that, we could solve for AY, which is negative 7 kilonewtons. All that means is later on, just remember to flip the direction, okay? But since we assumed it to be this way, let's keep it this way for the entire question, okay? Only in our final answer will we flip that, all right? Next, we just want to find dy. So we could do sigma fy equals 0. And from that, solve for dy. And we get 91 kilonewtons. Okay? So with that, we found all the forces we can find through global equilibrium, which means now we need to take apart the frame and solve for the internal forces at each of the pins, okay? So we have a couple of options. We could start with piece DCHE, okay, because we have some known values there, and then go to ABC, or we can go to piece BGF and then go to piece ABC. So in BGF, we'd attack knowing values at G because of the pulley there. We could find forces at B and then go to ABC and then find forces at C. Or with DCHE, we could find forces at C and then move on to get forces at B. Okay, so we were just going to follow one option for the solution, but just keep in mind there's multiple approaches to solving this type of problem, especially once you take apart the frame and try to analyze what you're solving for. Okay, so we're going to take the DCHE approach. Okay, so notice that DCHE has a pulley at H. So let's do this first. Let's resolve the forces in the pulley at H, transfer the forces to DCHE, and then we're going to find the forces that we need on member DCHE. Okay, so if I remember correctly, I think you got 4 marks just for the pulley transfer last year. So keep that in mind. There's still stuff from the first midterm that really applies. Okay, so here I just have an image of the pulley. Okay, we'll note the tension is continuous throughout. So 84 going down, 84 going to the side, and then we have HY equals, and we have HY going up and HX just pointing opposite directions. Hopefully from this we can all tell that HY equals HX equals 84 kilonewtons, okay? Hopefully this shouldn't be too much of an issue. Now let's transfer the forces onto the member. So if you'll note, just really quickly, I have HY and going up and HX going to the right on the pulley, which means when they're acting on the member, I just point them in the opposite direction, but of course I'm not going to change the magnitude value, the value itself, okay? So from that, let's start solving for what we need. So again, I have a picture of the free body diagram right here. So as you guys can tell, we want a member ABC. So the only relevant thing here is point C. So let's try to solve for values at point C, okay? So our first thing to do will be to take the moment about point E. This is because we don't need any values there, first of all. So by taking the moment there, those are eliminated automatically. And also, hy, cy, and dy become out of the picture because there's no arm for the force, okay? So from that, we write our equation. As I always like to do, solve the algebra first, isolate for what we need, then substitute our value in, and get our value for cx, okay? So if you know, we found cx. We want cy, but it's kind of difficult, actually very difficult to find cy, because if we take a moment at any point along, so you take a moment at D, moment at H, or moment at E, cy has no arm to that point. The line of action of the force coincides with the point we're taking the moment about. So it won't be useful to find it using this member, okay? So now we're going to move on because that's all that we can find quickly with this piece, okay? So let's look at ABC now. We know AY and we know CX, okay? We need to find BX, BY, and CY. So really quickly, we'll note that there's two forces in the X direction. So sigma Fx should be very simple right now. Sigma Fx equals 0. We'll note that 0 equals Bx minus Cx, just the way I've drawn it. Bx equals Cx, Bx equals 42 kilonewtons. From that, now we have Bx known, Cx known, and Ay known. Only two unknowns are By and Cy. So very simply, we can either take the moment at B, solve for C, or we can take the moment at C and then solve for B, and then vice versa. We can pick whichever approach we want. So I decided let's take moment about point B, write our moment equation. We'll find Cy equals minus Ay, substitute our value for Ay in. Cy equals 7 kilonewtons. From there, it should be very straightforward. We only have one unknown in the y direction, so sigma Fy equals 0. Write out our equilibrium equation. Isolate for what we want to find. Substitute our values in. Get our final answer. Okay, so now we've found everything that we actually need to. But if we leave our answer just like this, you'll only get, I think, 8 out of 12 marks. That's because they want the sketch for the final answer. So all that means is we're just going to redraw our answer in the sketch format asked for. Okay, so we have our sketch with the forces at each point pointed in their positive directions. Okay, so if you just assume something was pointing one way and it was negative, just flip the arrow for your final answer. Okay, so if we all remember for A, I assumed initially it was pointed upwards, but when pointed upwards, it was -7. So for our final answer, let's point it downwards, and then just write simply 7 kilonewtons, foregoing all negatives in our final answer. And with that, hopefully, you guys can all get a 12 out of 12 on your frames and pulleys questions. Thank you.
Well, I think Aziz has a question about why the pulley forces were in the same direction at point H. You want to quickly explain that?
Sorry, let me just
Yeah, reshare and then just go back.
Yep. Let me just like in different frame directions should be changed. Okay. Why the force? Okay, I think we did change it. Maybe it was just missed or something. Let me just reshare screen, just so there's no confusion with that. Okay. So if you'll note right here. Okay. So this is my pulley. I have HY going up and HX going to the right. But if you look on the frame, I did flip the directions just like we do. So when we're taking apart a frame, if you guys remember, there's one point common in the middle, they're each pointing in the opposite direction, okay? So make sure you are flipping the direction.
Your HY, it's just a small little typo. The HY should be down.
Okay, yeah, sorry.
That's why people got confused. Another thing that you might notice this is equivalent to is if you just take the 84 kilonewtons that are with the pulley, just move those to H. It's like consolidating the system. So the same thing, that radius is R, so the distances are the same. Essentially, the moments cancel each other out. It was just a quick trick that my professor taught me last year.
Okay,
just
sorry.
move that 84 to H, 84 to H. You don't need to change any directions. Just take the pulley forces.
Yeah, so yeah.
Same
That was
thing.
my bad on that. It was a small little oversight. It should be pointed downwards, okay? I will fix it right now while the presentation's going, so you guys have a better version on when you guys are looking at the PowerPoint. Okay, that's my bad. It should be pointed downwards on the image. Okay, that was my fault on that. All right.
Yeah. Next, I'll be talking about trusses and design calculations. Okay, so give me a second to set up. Chat box open too. So with the truss illustrated below, determine the force in members AD, CE, CF, and EH. Indicate if the members are in tension or in compression. Secondly, with members AD, CF, and EH, knowing that they're all made from the same circular cross-section of 64 millimeters external and a wall thickness of 6.4 millimeters. Firstly, determine if those aforementioned three members are safe, and also secondly, determine the elongation of member CF. Oh, you guys don't need to know about beam design? Okay, I'll just go straight into solving the truss itself then. Okay. So for solving the truss of the first part of the problem, which is solving the truss itself, you want to take the moment of the whole free body diagram of the truss and find its reactions at point G and point H. Then you want to draw free body diagrams of each specific point to find out what the member forces of AD, CE, CF, and EH. Then you can solve for those force members. The reason I recommend to always stick to that method is the fact that if you can't figure out what to use for a cross-section to figure out how to simplify doing this first part of the problem, it's always easier to do it point by point to like actually figure out what specifically the member forces are for the ones that you actually need to solve. So firstly, by taking all of the by looking at the whole free body diagram and taking the moment at H. Oh wait, actually before that, one of the first things that you notice in this problem is the fact that point G and point H are both pin connections. This makes it statically indeterminate for kind of the horizontal direction, but because of the fact that you know members EG is only allowing for like a vertical force to occur, that means G of X equals to 0, as to maintain symmetry, there is no horizontal reaction at point G. So then by looking at by taking the moment at point H and equating it to 0, you would find out that GY is specifically 42 kilonewtons going up. And then afterwards, by taking the sum of all forces horizontal and vertical and equating it to 0, you would find that HY is 12 kilonewtons going up, and the HX is 36 kilonewtons going right. Firstly, looking at point H, you want to try to find out what specifically members EH is. Because of the fact that you know EH has a vertical and horizontal component, by taking all of the horizontal forces, you would be able to isolate only for the unknown of EH to figure out what EH specifically is. With the correct proportions to the horizontal force, you would find out that EH is 36.9 kilonewtons in tension. Then taking the sum of all vertical forces and equating it to 0, you would find out that FH is 20 kilonewtons in compression. Then specifically looking at point E, similar to point H, you want to, because of the fact that you know CE has a vertical and horizontal component and EF only has a horizontal component, by taking all of the sum of all forces along the vertical direction, you only have one unknown, which is the vertical of CE, and you can find out that CE is specifically 42.5 kilonewtons in compression. One thing to always remember is to always correctly proportion it to what specifically the horizontal and vertical component of the force is. In this case, because of the fact that the height of member CE is 4 meters, the height of the width of member CE is 3 meters, and the hypotenuse is 5. The vertical component of CE is 4/5, which gives 42.5 kilonewtons in compression. Then looking at point B, you want to try to find out what the member force of AB is, so that you can use it in point A to be able to find out what member force AD specifically is. Because of the fact that there's three forces, the one going horizontal at AB, the one going diagonal towards the top left direction called BD, and the fact that there's a 54 kilonewtons force going down. If you take all of the horizontal and vertical forces, and you would find out you would have two different equations. One equation like with two unknowns, and this kind of forms like a linear system that you can easily solve, and you would be able to find out that BD is 62.5 kilonewtons in compression, and AB is 37.5 kilonewtons in compression as well. Then going into point A, you want to try and find out what member force AD is specifically is, and also AC. So you can use it at point C to find out what CF specifically is. Similarly, in point B again, by taking all of the vertical and horizontal forces and equating it to 0, you would find out that there's two unknowns again and two equations with AC and AD, and you can figure out what AC and AD specifically are, which is 60.324 kilonewtons in tension, and AC is 30.625 kilonewtons in compression. Then finally, looking specifically at point C, you want to try to find out what member CF is, because of the fact that you already know what AC specifically is, what CE specifically is as well from previous calculations in point H, point A, and point B, and point E, and also the fact that you know that CF is the only unknown with a horizontal component in terms of its force. By taking all of the horizontal forces and equating it to 0, you'll find out that CF is 36.9 kilonewtons in tension. So, so now that we've solved the first part of the problem, therefore AD is 60.324 kilonewtons in tension, CE is 36.9 kilonewtons in tension, EH is 36.9 kilonewtons in tension as well, and CF is 42.5 kilonewtons in compression. Because of the fact that this second part is all of the design calculations and you guys haven't learned it, I think we'll just skip that and head to the next section for the exam. I guess I'll just start answering the questions now, unless there aren't any. I think Awale has taken care of that. So I believe Masbin will be taking the presentation for the 3D reaction.
Yeah, just give me 1 second. I'm gonna share my screen. Can you guys see it? Like, oh, is it working?
All good. Yeah, we can see it.
Okay, yeah, sorry. Okay, so this question is in relation to 3D reactions. And usually, like, honestly, this question is supposed to be like I think it's usually the easiest on the exam. And if anything, like even when I present the solution, you'll sort of see that it doesn't require that much work. So if you're struggling on the exam and say you're time consumed, always try to collect your marks on this type of question first, because it isn't like too challenging. But yeah. So the question is, the rigid frame ABCD is supported by a ball and socket at joint at A, two cables CE and DF, and a roller support at D, which allows translations in the Y and Z directions. The frame can be assumed weightless, and the line of action of the 1,000 Newton force is parallel to the Z direction. Determine the magnitude of the force in each cable and express the forces in the cables in Cartesian vector format. So just like for any other question, especially for like 3D equilibrium and reaction questions, always draw the FBD diagram. There's definitely like some points allotted to that itself. So yeah, and I'll go to the next slide and then you'll see. So I actually directly copy pasted like my solutions because I did get like, perfect. I got 0.5 off, but I'll tell you guys like why I got 0.5 off. So if you look at the FBD on the top right corner, you can see that at point A, because it was a ball and socket, there are three reaction forces. There's the AX, AY, AZ. And then I have the two cables going from C to E and D to F. And then at D, recall they said that it allows translation in the Y and Z direction. So that means there's only an X component force at D, so dx. And then at B, there's that downward 1000 newtons force. So then, since we are trying to find out, well, what is like the tension force going from C to E and D to F, that's what we're gonna first write down. So as you can see, I wrote down, well, the tension in CE is going to be equal to the force from CE times the direction vector. And the direction vector, that should be sort of easy, so I'm not gonna go over. You're just gonna subtract like the coordinate CE from E all over its magnitude, which is square root 44. And then I did the same thing with the cable DF. So the tension in DF is going to be equal to force of DF times its direction vector. And then the force at B is just that downward 1000 newtons force. So it's just going to be 0, 0, negative 1000. And then once again, the force at D is only dx and then 0, 0. And then usually with all these questions, if you even do the past finals, you'll see that they always put a ball and socket, because the ball and socket has 3 reaction forces. And when you're solving those questions, you'll literally see that it's so repetitive. You're always going to take moment about wherever the ball and socket is. So in this case, the ball and socket is at A. So you're going to take the moment about A. And so the way that I think about it is, well, do you see that like bolded sort of like a T figure in the diagram that they gave us? So then I sort of think, well, like, okay, let me connect all the forces that we have, TCE, the tension at DF, the force at B, and force at D to that one point A. So how do I connect them all? So I'm going to find, say, the distance A to C. And that's what I did there, R, A to C. You just subtract the 2 coordinates, like 0, 0, 0, and 2, 6, 0. And then A to D, I found that, and then I found A to B. So now when you're trying to calculate the moment about A, all you're gonna do is, so let's look at our first force, the tension at C to E. What is it connected to from the 3 directions that we just calculated? Obviously, it's connected to point C, which is connected to the RAC. So you're gonna cross RAC, cross the tension at CE. And then you're gonna do plus RAD cross the tension DF. And then plus RAD cross the DX, because as you can see that RAD is connected to like point D, and then plus RAB cross the force at B. And then literally if you get to that step, you're like set in stone, you're like done practically, because the next part is like computational. All you're gonna do is cross multiplication. So do practice past midterms, because like I think that's the one place that you possibly can make a mistake. And then all you're gonna do, you simplify it and you get to this last phrase at the very bottom. Then what you're going to want to do is you're gonna do moment in the X direction, moment in the Y direction. And how do you do that? Well, you collect all the like terms from this one statement. So say we want to do moment in the X direction. From that last statement, you're going to take, so it'll be 12 times force of CE over square root 44 plus 12 times FD over square root 41 plus 0 plus negative 6,000. And you do the same thing. It's like, you know, you collect the I values and then the J values and then the K values. Yeah. And upon doing so, you get 2 equations. You get the moment X equation, moment Y equation. And because it's 2 equations and 2 unknowns, very easy to solve for the forces. I just simplified moment about Y, and then I got FDF in terms of FCE. So all you do now is you sub that into the moment in the X directions, and then when you simplify and collect like terms, you will get force of CE is equal to 1,105.547 newtons. And then you also get force of DF. But you're not done yet, because they ask for what is the tension in each cable. So remember those two equations at the very beginning that we came up with. At tension CE is equal to force of CE times its direction vector. Tension at DF is equal to force of DF times its direction vector. So now, since we know what force of CE is and force of DF, you're just gonna sub those values into those 2 equations. Oh, whoops. And when you do so, yeah, so remember they said put it in Cartesian vector form. So when you sub it in, what you'll do is, say the first one, tension at CE, you're gonna do 1,105 times 2 over square root 44, and that'll give you the I value, which is 333. And if you keep doing that, you'll get the I, J, K values. So always ensure you go back to the beginning of the question and see like what format does it ask you to put your final answer in. And so I remember this question was out of 12 and I got 11.5. The reason they took off 0.5 marks was, I don't know, it's kind of dumb, but they said I put too many significant digits, but I don't know, like they never even specified how many digits you need. So I probably could have appealed that if I wanted to, but you know, it doesn't matter. But they literally said I put too many significant digits. But yeah, that's basically it. This question isn't too hard. Like if you do past midterms and finals, you'll see they're all the same, like all the same process. But yeah, that's this question.
Okay, I guess that means it's my turn now. So I'm going to share my screen. Okay, can everyone see this?
Yeah, we can see it.
Okay, great. There we are. Shear and bending moment. Okay. So you guys aren't doing beam design. So I'm going to ignore part B and we're just going to focus on drawing bending moment diagrams. Okay. So this is probably the last thing that you guys have learned in the year, and it's probably a bit hard because it does take everything that you've learned so far and combines it into one thing. However, at the same time, this is probably the most practical application for everything you've learned. So I don't know, maybe kind of view it as like the fruits of your labor. You've learned all this to actually do something, and that's the cool thing that you can kind of do with it. With this question, you have a mass of 500 kilograms, which is that box right there. Okay, there. And it says that the beam is homogeneous and has a total mass of 80 kilograms. Don't forget to include that mass. When I was doing this question on the midterm, I forgot to include the mass, so all my answers were off. However, if you have the wrong FBD, as long as you draw out what FBD you used to solve the question, they're still going to give you marks for filling out the solution. So even though my free body diagram was wrong, I still got 7.5 of the marks out of the 12 available because I was able to fill everything out there. So even if you don't know what you're doing, state an assumption, carry through as well as you know. Okay, so in order to draw our shear and bending moment diagrams, first thing we need, of course, is that FBD. And the hardest thing for me was to think about how to deal with this tension force, but also that there's supposed to be some sort of force from the beam that's keeping this little mass up. And so what you can do is think about the block. The block needs to be at rest. It has its gravitational force, which is pulling it down, a tension force that's keeping it up, and then this force that I've labeled R, that is a force from the beam. And so by equilibrium, you can form an equation here, and now you can have that reaction force in terms of T. And so then we draw our FBD. We had that tension force. It was at an angle of 30. So you can consolidate that into its two parts, Tx and Ty. The weight of the beam is right at its centroid, which is at 1.5. So we have that 1 meter and then that 0.5 meters. Two reactions from Ax and Ay because it's a pin. And then finally that force that I labeled R, which is from the box onto the beam. And so what we'll do to solve for this is we'll get the moment at A. And we'll get the moment at A because everything else that is exposed by this moment is in terms of T. And so we'll have our equation here. We'll sub in the equation that we got from step 1. And we'll have everything in terms of T. And then we can solve for T, which is around 2,400. Now, once we know T, we can start to actually find the reactions for Ax and Ay. Ax is pretty straightforward because there's only one unknown there, which is going to be the T tension force. So you just solve for that. Ax just has to be in the opposite direction of that tensile force, which is around 2,100. Then Okay, that's cleared up now. We have the forces in the y direction. So we have our AY, we have that force from the box, we have the weight, and we have the tensile force. It's a bit longer, but still same thing. There's only one unknown there. You can rearrange it, and then you'll get 2040 for AY. And then now that we actually have our reaction forces, we can start to build our shear diagram. And here's one thing that threw off a couple of friends of mine. It tells you that the weight can be put at the centroid. And yes, it can be put at the centroid to make your calculations easier. But when you actually think about it practically, that weight is actually a distributed load. And so when you calculate that weight, it turns out to be 784 newtons. And that's 784 newtons over 3 meters. And so you can make that a distributed load. So that's actually 261 newtons per meter. And so we have our distributed load here. We have AY. So first thing for our shear diagram, the first force is AY. So we're going up 2040. And then after that, we're going down linearly because that's what a distributed load does. We're going down linearly. And then we're going to go down exactly 261. Why are we going down 261? Because it's 261 newtons per meter, and we went down, well, to the right by 1 meter. And so that's why we went down by 261. Then after that, we have our force R here. So we're going to just drop by the magnitude of that force, which is 2,472, which brings us at negative 693. And then finally, we're going to go down linearly because all that's left is that distributed load. And this time it's going to be about 522. And the reason for that being that it's once again 261 times now the length that we're going by is 2 meters. So that's why the magnitude's twice as much this time. And then finally, we're going to go up by 216 because that's the final reaction force, which is that tensile force. And so you might notice that if you do the actual math of my numbers that you're off by, I think like about 1. And the reason for that is due to all the rounding that we took. If I used like everything to the exact decimal, we would end perfectly at 0. If you notice that like you're off by 1 or something, you probably got it right. It's just the rounding. So just draw the line as is. This is exactly how Sika answered it in the exam answer key, so don't worry too much about your rounding there. And so now we actually have the shear diagram. The question now becomes to draw the bending moment diagram. And the bending moment diagram is your integral of your shear diagram. And I'm just going to check the chat to see if there's anything important. Okay. I mean, yeah, but it's a point load. Keep it easy because they didn't ask for a size of the box, but you're right. It would be a distributed load if it was for the box. And so you could do it in terms of like equations of these lines, but these are very simple geometric shapes. So you have your trapezoid. So break it up into a rectangle and a triangle, similar to those hydrostatic problems. And so we have our rectangle of 1779. The length is 1 meter, so 1779 times 1. Plus we have our triangle. The difference between 240 and 1779 is 261. So that's our height. Our width is 1 meter, and then divide by 2. So that's going to give us 1910 for area 1. Area 2, same thing, the rectangle, negative 693. And then after that, you have your width, which is 2. So you multiply that for the rectangle. And then for the triangle, that's going to be negative 523 times 2, because our base is 2, divide by 2 because it's a triangle. And that gives you 1910. And you might notice that the areas are supposed to be equal to each other because the areas should cancel each other out. One positive, one negative to equal 0. Once again, we're off by 1. That's due to rounding. And so when we actually draw the moment diagram, it was linear, which means that what we're going to have is actually a quadratic curve. So we draw our curve to 1910. So that's how much we increased. And then we draw another quadratic curve. We're decreasing by 1910 just to represent those two areas. Okay, I'm just going to check the questions because I see something in the chat. Okay. Okay, and then this is pretty much how to draw bending moment and shear diagrams. Everything else from here is just about beam design, which I'm assuming you don't need to know. But in general, you just take your maximum moment, and then you would have your moment of inertia, and then you need to find out what the largest y is. It doesn't really give you a cross-sectional area or like a cross-section. So the whole idea is you use something called the section modulus. If that sounds like gibberish to you, I'll just stop. If it's not, were you taught it or is it just not on your exam? Did you guys do beam design at all, or was it just not on your exam? Never taught it. Okay, moving on then. Then in that case, we are done because everything else from here is just talking about how to pick the right beam. So thanks for watching, guys. Like and subscribe. Thanks for coming. Have a nice exam jam. Best of luck for exams.
Yeah, so for the person who asked where's the recording, I'll get the recording like done as quickly as possible so that I can like send it to you all on the emails that you signed up. Hopefully you've signed up
Before you all leave.
yeah. If you didn't sign up, please use this link so that I can get your emails to be able to send you the recording.
Are you all in Civ? Because we've been trying to get like a Civ Discord started, but we can never find everyone because it's all online.
But yeah,
So I'm just gonna send an invite if that's okay.
join the Civ Discord server and also sign up using the Google Forms in case you haven't signed up, just for me to be able to send you guys the YouTube link. Yeah. Oh, also one last piece of advice is do all of the Civ 100 tests. Do it to a point where you don't have to think about it. So when you get it, you can just immediately like go bop bop boom and then like figure it out as quickly as possible.
Obviously, when it comes to exams and stuff, hard work is definitely going to help you do well. But I would like to point out that working yourself to the bone is also not going to help you, because if you're so burnt out and like you don't have the energy to actually write the exam in the given moment, all that preparation is for nothing. Do make sure that during this unusually compressed exam break, because of some things to do with the calendar that I won't explain, that you do take some time for yourself and your mental health to like take it easy a bit. Know when you need a break and take that break. A lot of the Civ 100 exams in particular are extremely repetitive. So like if you start to notice that like you're getting the hang of it, don't feel like, oh, I need to do every single year in existence so there's no surprises. If you feel you're confident and you feel you're at a certain level, move on to another subject that you feel that you're not so confident in. Just make sure that you're taking things easily, you're managing your time properly, and remember, put yourself first instead of your grades.
That's a nice conclusion. Thank you all.